Okay, to wrap up today, let's talk about how regularization can help us avoid this problem of gigantic lambdas in the case of linearly separable data, and then see how Roc curves and precision recall curves can allow us to compare two different models. Okay, so our problem is that when we optimized only this right here, which was the average cross-entropy loss, we end up getting betas that are huge. So to penalize huge betas, we're going to create what I'll call an empirical risk objective. Now, this particular set of equations I stole straight from last year's notebook, so some of the vector notation is gone, but I hope the basic idea is clear. So what I've added here is the regularization term that says, hey, if you have betas that are really big, that's going to increase your regularized risk. Now, how do I optimize this? Well, I compute its gradient, just like any other. Well, what's the gradient of the cross-entropy loss? It's this thing we had before, which we called risk gradient. And now we just need to add in 2 lambda beta. Why 2 lambda beta? Well, because the gradient of this over here is 2 lambda beta, where beta is a vector. Okay. So, quick notes. When we use regularization, we're not going to include the beta that corresponds to our bias term. Sometimes that's beta 0, sometimes beta 1. So I'm just putting beta 0 here. Okay. Mostly out of laziness. You know what? Let's fix it. Okay, we'll mix it. Just to match what we did in lecture today. We have arbitrarily chosen, by the way, to use accuracy as a way to compare our models. So we could use something else, as we'll see in a bit. And in the example below, I'm going to use the test error to assess the quality of a given lambda. But in real life, we'd probably use cross-validation instead. Okay, so this expression here, which is just the gradient of the average cross-entropy loss plus our penalty, is given by the following. So the L2 regularized gradient is the original gradient plus 2 lambda times non-bias betas. Why non-bias betas? Well, because of what I said here earlier. When used regularization, we don't want to include the weight of the bias term. Why? Well, I'm not sure we actually said this in lecture. Probably should have if we didn't. But that's because the reason we try to keep our beta small is we don't want to overemphasize any specific feature. However, our offset term or our bias weight, it's just it's an offset. So it's not that it's overemphasizing any specific feature. So this includes only the non-bias terms. Okay. Now again, I'm just going through things fairly quickly. Like the really, really important stuff in this lecture is what we took our time with. And this is just showing you what it might look like in code. But we would really need to spend more time with this and make it into homework and so forth for you to really fully digest this. So if you feel like this is a lot, which it is, that's fine. So what this does is it computes the regularized gradient. And then we're going to call gradient descent on that regularized gradient. Now, because there's many different possible lambdas here, we need to try a bunch out. And so as I said, we'd usually use cross-validation, but instead here I'm going to do just for every lambda, compute a different result. Okay. So if I run this big block of code, which you won't fully understand just staring at it, what it gives me is it says, when I pick lambda equals 0, that's unregularized, we get 100% training accuracy, but not perfect test accuracy. We overfit. Okay. Now, if we start setting up lambdas, we see that our training accuracy starts going down. Our beta sizes start going down. What this is right here is saying that the sum of the betas was 1,387 with no lambda. Now it's 670. As I increase lambda, my betas are going to get smaller and smaller. And we see that our test accuracy is going up. And it goes up, and it actually gets up to 96%. So by restricting the sizes of our betas, we avoid overfitting. Yes, we do slightly worse on the training set, but we do better on the test set. We keep going. We see that the test accuracy is still the same, but eventually starts falling off when lambdas get big. So here we're over-penalizing our betas, and we're adding too much bias to our model. Okay. So what we see here, if we look at these test accuracies, is the bias variance trade-off. At first, the variance of the model is very high, but the bias is very low. Over time, the bias goes up and up, the variance goes down and down, and so there's a crossover point where the model will be best. Okay. Now the best lambda then is maybe 0.001. That's equally good to say 0.01, but this is the best one that just my arbitrary search happened to find. Okay. Now I should note that 0.001 is not necessarily the very best lambda. It's just the best one that we tried. I happened to do a bigger test that wasn't here, and I saw that 0.006 yielded an even better accuracy. Okay. Now to do the same thing in scikit-learn, we could use Logistic Regression Cv. You've never seen this in our class. I'm just showing you briefly that I can give it a list of C's, and it will come up with the same accuracy that we did. Okay. So it does basically the same process we did. One quick difference, if you do actually end up looking at this later, is that C is the opposite of lambda. And that's because their regularization term is 1 over C times the sum of the beta squareds. So a larger C is less regularization. Okay. So I hope that seems cool. We actually did regularization using our own gradient descent from scratch and got the same thing we got out of scikit-learn. Okay, one last thing. So of course, accuracy is not the whole story. We also want to look at maybe our true positive and false positive rates, or our precision and our recall. And so I'm not going to go through this in a lot of detail because it's similar to code that you yourself have written, but I can see what my false positive rates and true positive rates are as a function of my threshold on a given model. Okay, so as I increase my threshold, my false positive and true positive rates go to 0, like we saw at the Roc curves. And we can actually just plot the Roc curve itself. Here's code that does it. And this shows that on my test data, my model that uses all the features has a Roc curve that looks like this. So the area under this Roc curve is quite good. If we also plot the one feature model, we see that it has a Roc curve that's not bad. I mean, it's still pretty good actually. But the all features model is actually better. Right? So we see we get this curve here. So the area under the all features curve is better. And so it's another way of showing that the all features model is better than the one features model. Before we looked at only accuracies, now we get a richer picture that compares the two models. And in this case, we get a threshold independent comparison of the models, whereas before we were relying on some specific fixed threshold. All right, and lastly, precision recall curves. So we can also plot the precision and the recall, just in case you're curious what that might look like. So I scroll down here. This is the precision recall on my scaled model that uses all of the available features. And if we plot that along with the one feature model, we see we get better precision recall curve for the all features model. Remember, where we really want to be is perfect precision and perfect recall. And this suggests that the all features model is much more likely, depending on the threshold we pick, to get us to a good point in our space. Okay, so that is it for this demo. Now I know that demo was quite a lot to digest, okay? But what I really wanted to do is give you this as a future reference so that when you are moving forwards with building stuff on your own, you can see that the tools we used in this class really do work, and you can see some of the little nitpicky details that might come up in a real-world implementation. Though to be quite honest, in your life, you'll probably be most likely to use scikit-learn without having to go all the way to the bottom. And that's part of the reason we haven't really emphasized that in the homework in this class. Okay, so very last thing I want to do is summarize today's lecture. I should mention that there's a little bit of extra material if you're curious about what you do if you have multiple classes, but I don't want to cover it in this video, and I just have the slides there if you're curious. So, at the very end here, to summarize, if we have a logistic regression model, we can take probabilities and turn them into classes with a threshold. The boundary between where we get zeros and ones is the decision boundary, and with logistic regression, that boundary will always be linear. In 1 dimension, it'll be a point. In 2 dimensions, it'll be a plane. In 3 dimensions, it'll be separating space, and so forth. And dimensionality, I should mention, is the number of inputs. So 2-dimensional model is 2 features. That would be like our flower classification earlier. We had a line and space separating them. If your data can be perfectly separated by a linear decision boundary. It's linearly separable, and that's going to cause your logistic regression parameters to get very big. So if you don't want that to happen, you should use regularization, and if you're doing that, don't forget to scale your data. We saw there's many ways to evaluate your classifier's quality. You've got accuracy, precision, recall, true positive rate, false positive rate, and the area under the Roc curve. But we also had some visual pictures. So that summarizes everything we did today. We also saw that very long demo. I hope you found it useful. Sorry today went quite long compared to what I was expecting, but I hope that you've enjoyed these re-recorded videos and that they gave you something useful that the not as good but much shorter version in lecture was able to achieve. All right, see you in the future, and that's all I got. See you then.